is Lester Smith here. I want to embarrass somebody. There's Lester Smith. Okay? Lester Smith has decided to be intellectually curious. So he sent me a request and he said, can you make any suggestions for other books written for this kind of audience on modern astronomy and astrophysics, because he wants to know more. So I put together a handout with some books. Norma will have the handout, I guess, on the table outside after class, since she's not here yet. There are a number of popular books that I would highly recommend you not read. Okay? But because this is being videoed, I'm not going to say what those are. But the handout will give you some guidance on books I think are good ones to read, and also ones that I think you might want to stay away from. Right? So go for it. And thank you, Lester. By the way, if any of you have questions for me, I think you have my email. If not, you can find my email, because it's just my name at vanderbilt.edu. And you're welcome to send me questions. I've gotten a good number of questions over the last few weeks, and I'm happy to get them. And if I don't have time to answer them, you won't hear from me. If I have time, you'll hear from me. So it's pretty simple. But I'm happy to get the questions. We ready to go? Again, for you folks coming in just now, that screen doesn't work. So if you want to do the Southwest Airlines thing and fill in the middle seats over here, we've got some seats over here. If you want to sit over there, your choice. So I'll go ahead and get started. The person I want to introduce you to today, to start off, is Henrietta Swan Leavitt, who, in my opinion, did the most important work in astronomy that was done in the 20th century. She is not as famous as she should be. So there are at least 100 people more today than yesterday who now know her name. She went to Radcliffe, graduated in 1892. With a degree from Radcliffe in 1892 as a woman, she was qualified to do nothing. She got a job working as a volunteer computer at Harvard College. Microphone went again. Try again. Again. Hello? 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 They're having electronics problems here today. This is on. Hello? Hello? Anybody home? Anything? Are we having fun yet? Hello? It came back. Are we back? Okay. So she was able to get a job after graduation as a volunteer, not a paid employee, a volunteer computer at the Harvard College Observatory. Again, I think we mentioned computers before in the context of the early 20th century, late 19th century. Computers were people who did computing, okay, the hard work. Her job was to search for objects called variable stars. Harvard had begun a project in which, using a telescope in South America, they took images of the sky, night after night after night. These images were made on photographic plates. Now, you folks actually know what film is for a camera. My students today have no clue what I'm talking about. Okay? Astronomers 100 years ago were able to get companies like Kodak to put the emulsions that are on film onto big pieces of glass, which would be put at the focal plane of the telescope, and the image would be produced on that big piece of glass. That piece of glass was then shipped back to Boston and put in a basement. And the director of the Harvard College Observatory hired people like Henrietta Leavitt to look at these photographic plates. And her job was to look for variable stars, which means stars whose brightnesses change. So tonight it'll be bright, tomorrow it won't be as bright. And some stars are the same brightness all the time, and other stars, losing it again? Hello? Hello, am I here? I'm going to keep trying, but this isn't going to go. bright, faint, and back again. It cycles like this. Myra happens to be a star known as a regular periodic variable. It varies in brightness very regularly, very periodically. You can calculate how long it takes to go from brightest to faintest to brightest again. That's the period of the star. Thank you, sir.
That won't help for the room. But
can you hear me?
that's just for me.
That's just for you. So I have to keep shouting. Okay. We'll keep doing that. This is an easy variable star. There are lots of different ways in which the brightnesses of stars can vary. If you have two stars in a binary system with one going in front of the other, one will block the light from one star, so the system will get fainter, and then when it unblocks the light, the system will get brighter again. Lots and lots of different ways in which stars can be variable. The particular kind of variable star that Henrietta Leavitt found and made her money from, in effect, is the star known as Delta Cephei. The prototype of the stars known as Cepheid variable stars is this one, Delta Cephei, found in 1784 by John Goodricke. He discovered this by accident. He noticed that it changed in brightness. This is before photography, so this is just measuring it by eye. But he noticed that it got brighter and fainter and brighter and fainter. And it does so in a very peculiar way. So this is actual data for Delta Cephei. And again, the vertical axis is brightness, the horizontal axis is time, and you see it goes from minimum brightness up to maximum brightness and then down again. And the one on the left is a cartoon of what that periodicity looks like. It doesn't just smoothly get brighter and smoothly get fainter. It actually gets brighter very rapidly. It gets brighter much faster than it fades away. So the upward slope is much steeper and it takes only a day, whereas the downward slope is shallower and takes about 4 days. So it gets bright quickly and fades away slowly. In addition, as it fades away, well, as it gets brighter, that's a very smooth increase in brightness. It just gets brighter and brighter and brighter and brighter until it reaches maximum brightness. When it fades away, and then it kind of hits a bump right here, where it stops fading as slowly. It's still fading, but it fades at a different rate. And then it steepens again. And then it hits this little plateau, and then it falls off again. It's a very peculiar way in which this star brightens and fades. Yes, sir?
How was the brightness measured at that time?
Well, by Goodricke, the brightness was measured by saying, oh, it looks bright, now it looks faint. By Henrietta Swan Leavitt, it was still done by eye. But she and folks who did the kind of work she did trained themselves to be able to say, that looks twice as bright, that looks 3 times as bright. It wasn't very quantifiable in a modern way, but nevertheless, they were pretty good at this. And if you know the relative change in brightness, that's going to be good enough to identify this kind of star. So this variability pattern is different from this one, because this one's smooth up and smooth down and smooth up and smooth down. This one's very different, easy to identify. Now, it's easy to identify once you find the star and make all the measurements to identify them. That's the hard job. Henrietta Swan Leavitt was really good at identifying these kinds of stars. Over a period of about 6 years, from 1904 to 1910, she identified more than 2,000 variable stars in 2 groups of stars known as the large and small Nlagellanic Clouds. The large ones on your left, the small ones on your right, little fuzzy things in the southern sky. You can't see them from Nashville. But if you go to the southern hemisphere, you'll see them. They were first identified by a European, by the sailors on Magellan's ship, hence the names the Nlagellanic Clouds. They might have had some other name before that, but this is what we now call them. These were not all Cepheid variable stars. These were just stars whose brightness is changed in these clouds. Yes?
Does she get a glass plate for every day of the week? Is that how she knows?
She had a glass plate for every day in which measurements were taken. That might have been every day of 1 week, and then it got cloudy. It might have been that this week they observed the Large Magellanic Cloud and next week the Small Magellanic Cloud. Depends on what the astronomers were assigned to do at the time. And they didn't have just one field of view, as we would call it, to observe. But she received probably at least 100 plates for this part of the sky for a year, and over and over and over again for a number of years. So she found 2,400 variable stars in these clouds. Of these, 25 of them appeared to be Cepheid variable stars. They did not yet have the name Cepheid variable stars. That name was not coined yet. But 25 of them, she said, had a peculiar pattern, and they had the pattern we just saw, but she discovered something more important than that. And this is from the paper that was produced with her results, the Harvard College Observatory Circular number 173 from I believe this is 1908, though it might be 1912. And she writes, the following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt. That was very nice. She got credit in the footnote, if you will. The author of the paper was not Miss Leavitt. She did all the work. Okay? And this was the way in which she was acknowledged for having prepared everything. Okay? But what she found is that for those 25 variable stars, who all varied in the same kind of way, there was a very special additional pattern. And that's illustrated by this plot, which is from her paper. Again, the vertical axis is brightness. The brightest stars are at the top. The faintest stars are at the bottom. The horizontal axis is time, going from 0 days to 120 days. The time measures how long it takes the stars to go from minimum to maximum and back to minimum brightness again, the period of the variability. All right? And what she found is that the period of variability depended on the brightness of the star. So over here on the left, we have the faint stars. Each dot is a star. We have a faint star here who varies with a period of about 2 days. Up here on the top right, we have a star that's much, much brighter, hundreds of times brighter, with a period of about 130 days. The brighter the star, the longer it takes to get bright and faint and bright again. The fainter the star, the more quickly it can change from bright to faint to bright. Yes?
Do those faint and bright numbers, are they always the same, or do they vary?
For any given star, the question is, do these numbers vary? Do the brightness periods vary? For the star whose brightness is 2 days, it's always 2 days. For the star whose brightness is 20 days, it's always 20 days. For the star's brightness is 120 days, it's always 120 days.
Is it always the same level of brightness?
That was the question. Was it always the same level of brightness? Henrietta Leavitt effectively asserted that it would be, and yes, it turns out it is. For those given stars, it's always the same level of brightness. But that's truly the power of what comes out of this plot. So all she discovered at this point is that for this particular kind of variable star, not for others, but for this particular kind of variable star, the Cepheids, the period of variability depends on the brightness of the star. The brightest stars take a long time to change. The faint stars change very quickly. This plot right here, this is a curve on here. The reason for that is because of the way in which the brightness and the time period are correlated. This axis is actually what we call linear. It just goes 0, 20, 40, 60 in a straight line. The vertical axis, the way astronomers measure magnitudes, is not linear. So when you go from 16th magnitude to 15th magnitude, the brightness is changed by a factor of 2.5, not by 1. So it's a curvy line. This is a different way of plotting the same data, the exact same data, but now the brightness is still on this logarithmic, as it's called, scale, and she's done the same thing with time. So 0 is a period of 1 day, 1 is a period of 10 days, 2 is a period of 100 days, and on this plot, which is called a log-log plot, you get a straight line. It's easier to see the correlation. The math doesn't matter for us. But again, each data point is a star. The lines through the data are her fits to the data points. The reason there are two lines, the lower line is for measurements of the stars when they're faint, at their faintest moment. The top line is measurements of the stars when they're at their brightest. You need to make sure you're comparing apples and apples. So you can compare stars that are bright or compare the stars when they're faint, but you want to make sure you compare the right time for each object. So she wrote in this paper, since the variables are probably at nearly the same distance from the Earth. All right, let me come back. Here are the Magellanic Clouds. Remember we talked about star clusters last time, or 2 times ago, or sometime. What she didn't know is that these are galaxies. The word galaxy really didn't exist in a modern sense then. These are galaxies, but they're giant collections of stars. And what did we learn about giant collections of stars last time in terms of how far away the stars in those clusters are? Nearly the same distance. I don't yet know the distance to either one of those collections of stars, but I know that all the stars in the Large Magellanic Cloud are at about the same distance from us. All right? So if they're at about the same distance, she writes, their periods are apparently associated with their actual emission of light. This is an incredibly important statement. If the stars are at random distances from us, then the bright stars might be close, and the faint stars might be far away. Or the bright stars might be far away, and the faint stars might be close. But she doesn't, although she doesn't know the distance, she knows they're all essentially at the same distance. And therefore, the bright ones truly are brighter than the faint ones. All right? That's a very, very important part of this puzzle. She then writes, it is to be hoped also that the parallaxes of some variables of this type may be measured. She doesn't know the distance. It's not in her job description to figure out the distance to these clusters. But if someone could just figure out the distance, then on this plot, these brightnesses would be absolute brightnesses. We would know that the bright ones are 400-watt light bulbs and the faint ones are 10-watt light bulbs. If we don't know the distances, we don't know how bright the stars actually are. We just know the bright ones are brighter, the faint ones are fainter. But if somebody could measure the distances and calibrate the brightnesses, then we're going to know something incredibly important, because we're going to know how to measure the brightness of any object that is a Cepheid variable star. This is a modern chart of what is now called the period luminosity relationship. It relates the period of the Cepheid variable stars, how long it takes to go from faint to bright to faint, to the luminosity. In this case, the luminosity is plotted relative to the brightness of the sun. So right here, something would be 10 times brighter than the sun, 100 times brighter than the sun, 1,000, 10,000 times brighter than the sun, etc. And we also now know that there are actually 2 different types of Cepheid variable stars. They're known as type 1 and type 2 because astronomers are very imaginative with their language. So for modern astronomers, it's not enough just to identify it as a Cepheid. We have to look more closely to know whether it's a type 1 or a type 2 Cepheid. But having done that, and we know how to do that, all type 1 Cepheids behave in the same way. They all follow that top line. And the ones that have a variability period of 5 days are about 2,000 times brighter than the sun. The ones that have a variability period of 30 days are about 25,000 times brighter than the sun. 25,000. Right? I'm just reading my plot there. They're very bright. That's important too. The question that was asked a few moments ago is, do they all have the same brightness? Or at least, does a star that has a period of 100 days always have the same brightness? Not only does that star always have the same brightness at maximum light, let's say, but every Cepheid variable star that has a period of 100 days will have the same brightness as every other Cepheid variable star that has a period of 100 days. Having measured now or calibrated the brightnesses of those stars, I can learn something else. See if you can get this for me. If I know how bright the star looks, I measure it, I identify it as a Cepheid variable star by its light curve, by the way at which it gets brighter and fainter. And I say, ah, that's a Cepheid variable star. I determine that that particular Cepheid has a period of 20 days, and it's a type 1 Cepheid. I look up on this plot and I say, oh, it has an absolute brightness 10,000 times brighter than the sun. Well, every Cepheid variable star isn't the same distance, but you're getting there. If I know its absolute brightness from this plot, and I know its apparent brightness because I'm looking out in the sky to say how bright it is, what have I now determined? The distance. Yes, in some sense, the absolute brightness here tells me the energy it's putting out. But the key for us is if I know how bright it looks and I know how bright it is, I know the distance to the star. Remember our light bulb. If I have a faint light bulb and I put it in front of your nose, you say, whoa, it's bright. Okay? But it's not really bright. In order to know the true brightness, I need to know the distance. So if I have a faint object and you know the distance, you can calculate its true brightness. If you know its true brightness and its apparent brightness, you can calculate its distance. This plot enables me to measure the distance to any Cepheid variable star because they're all the same. Every Cepheid variable star with a period of 20 days will have the same brightness as every other Cepheid variable star with a period of 20 days. And I've now measured the absolute brightness of that Cepheid variable star. So now all I have to do is look out in the sky and find myself a Cepheid variable star, figure out where it fits on this plot. I know its apparent brightness, its absolute brightness. I get its distance. This is the most powerful tool astronomers have now for measuring distances, large distances. Here's another HR diagram. We've seen this lots of times. Again, we have the temperature of the star, hot stars to the left, cool stars to the right. Brightness of the stars measured in the luminosity of the sun. The faintest ones are about 100,000 times fainter than the sun. The brightest ones at the top are about 1,000,000 times brighter than the sun. We have our main sequence going up through the middle of the diagram. We have something new on this HR diagram. It's up at the top, and it's called the Instability Strip. Any star that lands in the Instability Strip is unstable. How about that? Okay. Now, we know that most stars spend most of their lifetime on the main sequence. We know about the white dwarfs that live down here, the lower left. Those are stars that have died. We know that at the top right, we get the red giant stars, stars that are on their way to becoming white dwarfs, but they have to expand and get really bright and big and cool before they can shed their outer shells and become white dwarfs. When stars start to die and they leave the main sequence, a lot of them will pass through this instability strip as they evolve into red giants. In that particular part of the HR diagram, or if you will, in that particular time period in the evolution of these stars, they become unstable. And what happens is they pulsate. They get bigger and smaller and bigger and smaller. They actually move up and down this strip because when a star gets bigger, it moves up to the right. And when it gets bigger, it will get cooler, which moves it off to the right. So they move upwards to the right when they expand and cool off. And then when they get too big, their size makes them again unstable and they shrink again. And when they shrink, they become smaller and hotter, so they move down toward the left. Stars do this because of the way light is trying to escape from the stars. There are certain time periods when the light from deeper inside the star can get right through the outer atmosphere and escape to space. And when it does that, the star cools off very quickly. It loses energy. And when it does that, the outer part of the star will get smaller. It'll shrink. Like that hot air balloon that cools off, it'll start to collapse. When it cools off, the atmosphere of the star changes. And it changes and it becomes opaque to the light from inside. And when that happens, the light from inside can't escape from the star. So the atmosphere absorbs the energy and heats up. So the star expands. And when it expands, the atmosphere changes and becomes transparent to the light. So the light just escapes. So it cools off and it shrinks. And it does this for a long amount of time. And in the instability strip, that's where we find the Cepheids. I've got some notes down here on the bottom left that say the longest period Cepheids are at the top of the instability strip. So look at this instability strip, go to the very top where it has this label that says Cepheids with periods of days. The ones with the longest periods are at the very top. The ones at the very top are the brightest ones, because the further up we go on this diagram, the brightest the stars get. In fact, the stars at the very top of the instability strip are at the very top of the HR diagram. They are as bright as any star can possibly be. Short of blowing itself up as a supernova, these are the brightest stars we can find. Not only are they incredibly bright, we can identify them fairly easily because of the way they change in brightness. So why is all of that a great opportunity for astronomers? What is the value in knowing which stars are the brightest stars we can possibly find? Not the age. The distance. What about the distance? What's true about stars that are incredibly bright with reference to their distance and my ability to observe them? I can see them further away. If I want to find a star that's incredibly far away, I want to know which ones are the brightest ones, intrinsically brightest, because I will be able to see those stars when they're far away. A faint star that does this kind of brightness changing, well, that's great, but if I can only see it next door, that doesn't help me. If the star intrinsically is just as bright as a star can be, I can see those stars when they're incredibly far away. But from this diagram, it doesn't matter how far away they are. If I can measure their period, I know how bright they truly are. So I can find the distance to objects that are incredibly far away if they're Cepheid variable stars. That's the power of the Cepheid variable stars. They are great ways to measure distances to things that are very, very far away. So now I want to drop back into history a little bit again to move forward to tell you why these Cepheid variable stars are going to give us an age to the universe. So a little bit of history for us. In the 1840s, the Earl of Parsons in Ireland built what was then the biggest telescope in the world. Not a photograph, okay, but that's what his telescope looked like. It was a big thing. With that telescope, he started to observe objects that other people couldn't see very well. The bigger the telescope, the more detail you can see. And he observed this object that we now call the Whirlpool Galaxy. It's actually two galaxies that are interacting. There's a lane of gas that connects the top right one to the top left one. This is Lord Rosse's sketch of the Whirlpool Galaxy. And you can see the same structure. You can see this bar that connects the big one to the little one. It's a really nice sketch. Nobody knew what this object was, but there were two different points of view as to what these objects might be. One argument was they're newborn stars. It's a cloud of gas, and the gas is collapsing to make a star at the center, and as it collapses to make the star at the center, it starts swirling around. And it gets this swirling shape, like a pinwheel or like a water sprinkler. That was one idea. And in the late 18th century, before this time, astronomers developed their theories for how stars are born, and that theory predicted that newborn clouds that form stars ought to look like this. So this was a good idea, but it wasn't the only idea. The second hypothesis is that these objects are island universes. Again, at this time, the word galaxy didn't exist the way we use it today. They were referred to as island universes, that the Milky Way is one universe, and that these objects are other Milky Ways, other, to use the modern term, other galaxies far, far away. Nobody could figure out which was the right answer in the 19th century. In the 20th century, the early 20th century, this debate over island universes was the most important problem in astronomy. What is the right answer? And the person who led us to figure out the answer, though initially he actually got it wrong, was Harlow Shapley. Harlow Shapley got his PhD in 1914 working with Henry Norris Russell. Henry Norris Russell of the Hertzsprung-Russell diagram. So Shapley is doing his PhD work with the 800-pound gorilla of American astronomy, and he becomes the next 800-pound gorilla of American astronomy. After finishing his PhD, he went out to California to Mount Wilson Observatory, which in 1914 had the biggest telescope on Earth. That was 60 inches across. Now, I just told you that Earl of Parsons had an even bigger one, 72 inches, but it wasn't still around in 1914. So in 1914, the biggest telescope on the planet was the 60-inch telescope on Mount Wilson. In 1917, 3 years later, the biggest telescope on the planet was the 100-inch telescope on Mount Wilson. So Harlow Shapley went where he had the biggest toys to play with. Question? These are reflecting telescopes, yes. Reflecting telescopes means the light bounces off a mirror rather than goes through a piece of glass. In 1913 and 1914, before Shapley had actually finished his PhD, he and Hertzsprung of the Hertzsprung-Russell diagram, independently measured distances to several Cepheid variable stars. They calibrated the absolute brightnesses of Cepheid variable stars. So it was in 1912 that Henrietta Leavitt had said, if somebody could just calibrate this diagram, if somebody could figure out the distances to some of these stars, we'd have the whole diagram calibrated. And if we have the whole diagram calibrated, we can use this period luminosity relationship effectively to figure out the distances to any object in the universe that contains a Cepheid variable star. So Shapley contributed to calibrating that diagram, and then in the years 1915 to 17, working at Mount Wilson, Shapley identified Cepheid variable stars in 5 different globular clusters. So here's M13, a globular cluster. We talked about them last time. These globular clusters have hundreds of thousands of stars. They're tightly bound clusters of stars that can hold themselves together for the age of the universe. Within 5 of these clusters, he found Cepheids. Therefore, what does he now know for these 5 globular clusters? Their distances. By finding even one Cepheid in that cluster, he knows the distance to the cluster. And from that, he does something pretty amazing. He does what we would call bootstrapping. He now has a tool to identify brightnesses of those 5 clusters. He then looked at those 5 clusters, and he found that the brightest stars in those 5 clusters were all the same brightness. So let me give you an analogy for why this is going to work. In this room, there are maybe 100 of you. How many of you are taller than 6 feet? 1, 2, 3, 4, 5, 6 of you. I bet if I collected a random assortment of 100 other people, if I go downstairs to the cafeteria and get the attention of the students and say, how many of you are taller than 6 feet? I'll probably get 6 out of 100. They're younger. All right, I'll get more. So, fair enough. If I find any random collection of 100 people who are not as young as today's college students, I'll get 6 out of 100. I don't know which 6 of you it'll be before the game starts, but I'll get 6 of you. Something I can probably count on. What he concluded is that in any star cluster, you'll have faint stars and bright stars, but the 25 brightest stars in that cluster will almost certainly have the same absolute brightness as the 25 brightest stars in that cluster. It's not unreasonable. But he can test that hypothesis because he knows the distance to that cluster from the Cepheid variable stars. So he knows the absolute brightness of the 25 brightest stars in that cluster. And he knows the brightness or the distance to that cluster because it has a Cepheid variable star. So he knows the absolute brightness of the 25 brightest stars in that cluster. And they're the same. And for those 5 clusters for which he had distances from the Cepheids, he was able to demonstrate rigorously that the 25 brightest stars in a cluster are always the same brightness as the 25 brightest stars in another cluster. Now, would this have been the same answer if he picked 5 instead of 25, or 400 instead of 25? I don't know. Probably. But he picked 25, and it's the right answer. Now, what do you do with that? Well, here's another star cluster. I can't find a Cepheid variable star in that star cluster, but I can identify the 25 brightest stars in that cluster, and I know they're the same brightness as the 25 brightest stars in that cluster. So I know the absolute brightness of those 25 stars, and I've just measured the apparent brightness of those 25 stars, so I get a distance to that cluster. So I've used the Cepheid variable stars on the 5 clusters I know to calibrate a secondary measurement for distance, which I'll then use for those other clusters. And he was able to use this average brightness of the 25 brightness stars to estimate distances to additional clusters. He then did this again with a different technique. Now, for this one, I won't ask for hands. But somewhere in this room are the 5 biggest people. Okay? Now, for Shapley, by biggest, he didn't really mean weight, though it would have that same effect. He actually meant how big do they look on the sky. Some of them are as big as the moon. Some of them are really tiny. However, he thought they're probably all the same physical size. The ones that look big are close. The ones that look small are far away. They're all clusters of hundreds of thousands of stars. It's probably gravity that's determining the actual size of this cluster. And he could test that because he now knows the brightnesses or the distances to those 5 clusters with Cepheids, and he knows the distances to a couple dozen more clusters in which he can identify the 25 brightest stars. And he can look at those clusters and say, how big is that one? How big is that one? And he finds that the brightness the size depends on the distance. Not surprising, but you have to demonstrate it's right, and he did. And that meant by measuring the angular size of the cluster as it looks on the sky, he was able to infer the distance to several dozen more clusters. There were 67 clusters that he could identify distances using one of these 3 methods. And from that, he put together this diagram. Each of the dots in this diagram is the location of a globular cluster. The horizontal axis is distance from us. So where the 2 lines intersect at 0, 0 on this plot, that's us. That's where the sun is. So we've got a sun at that point. And each of those dots represent where the globular clusters are as seen by us. In the horizontal direction, we're looking through the plane of the Milky Way galaxy. In the vertical direction, we're looking upwards out of the plane of the Milky Way galaxy. The units, you see 10, 20, 30, 40, these are units of kiloparsecs. 1 parsec is about 3 light years. 1 kiloparsec would be about 3,000 light years. So 10 kiloparsecs is about 30,000 light years. So most of these globular clusters are at significant distances from us, tens of thousands of light years. What Shapley recognized from this plot is that the dots are in a strange place. Where are most of the dots relative to the sun? Over to the right. The sun is not in the middle of this distribution. That's kind of odd, because obviously the sun is at the center of the universe. They ought to be distributed randomly in every direction. It's easy for us to laugh at that now. But at this time, nobody had ever conceived of the idea that the sun was not at least close to the center of the universe. When Copernicus said the Earth goes around the sun, that moved the center of the universe from the Earth to the sun. But there was no evidence prior to this that the sun wasn't pretty close to the center of the universe. This was the evidence that that was wrong. The sun is not near the center of the universe. Shapley concluded that each of these dots represents a group of hundreds of thousands of stars. These are big, massive objects. They're not single stars like the sun. He said the X is the center of the distribution of the globular clusters. The center of the distribution of the globular clusters must be the center of the Milky Way. So he effectively moved the center of the Milky Way about 15 kiloparsecs from us, tens of thousands of light years from us. He moved the sun from effectively the center of the universe to a distance 30, 40,000 light years from the center of the universe. Philosophically, that's a huge change, but it didn't bother anybody at the time. So the sun is in the suburbs of the Milky Way. Shapley concluded that the size of the Milky Way was so big that those spiral things, those island universes, were inside the Milky Way. In fact, he had measurements of the distances to the small and the large Magellanic Clouds because they have Cepheids. And based on this plot, the large and small Magellanic Clouds are inside the Milky Way. And from that, he concluded that all of those nebulae are inside the Milky Way and that the Milky Way is the entire universe. And he was wrong because he had calibrated his distances wrong. So the galaxy is not this big. And the large and small Magellanic Clouds are actually outside the galaxy. But it would take another decade to figure that out. So 1917, Shapley identifies the Milky Way as this structure for which the globular clusters can tell us where the center is. The sun has moved off from the center, and we have some new ideas to work with. All right, now Edwin Hubble comes along. Edwin Hubble is the kind of guy nobody likes, okay? Because he's just too good at everything. So he was state champion in the high jump and, of course, set the state record in the high jump. He then went on to the University of Chicago and played on Big Ten championship teams in both track and basketball. And then he, of course, became a Rhodes Scholar, okay? And when he went to England, he was a star in track, water polo, boxing, while he studied law. Okay? Go figure. Okay? So then he comes back stateside, and he actually became a high school teacher. Okay? He returned to Louisville, Kentucky, and taught Spanish and physics. And he did that for about a year before he decided, this isn't it for me. Okay? So he left high school teaching and returned to the University of Chicago and got his PhD in 1917. Immediately upon defending his dissertation, he enlisted and went to Europe to serve in World War I. He never actually fought in a battle, but I believe he became commissioned as a captain eventually. When he left the Army in 1919, he came back and returned stateside to Mount Wilson Observatory, where Shapley had just done all his work, where the biggest telescopes in the world were. So this is Hubble. Okay. This is Mount Wilson Observatory. This is the 100-inch telescope that he used to do the observations he had to make. The primary mirror is down here. The light comes down through the telescope, bounces off that mirror, goes back up to here. The best way to do astronomy at the time was to actually have your photographic plate, your camera, up here. But as you may have noticed, the stars rise and the stars set because the Earth rotates. So if you just take a picture of the sky and you take a long time exposure, everything blurs. And somebody in here has their own picture of Comet Hale-Bopp. Where's our Hale-Bopp picture? No? Oh, we don't have to get it right now. But somewhere in here is a picture that one of your classmates took of Comet Hale-Bopp. And because it's a time exposure, you actually see the stars as lines because they blur in the time exposure. Well, astronomers don't want to do that if they can help it. They want the stars to be little points. And to fix that, you have to track the telescope with the stars. As the Earth rotates, you make the telescope go the other way. So you have a little controller that helps you do that. But Edwin Hubble had to sit up here in what was called the prime focus cage to guide the telescope. For whole nights, he would sit up there, probably with his legs crossed. So that's how he took his data, working up in the top of that telescope. In October of 1923, he wrote a letter to Harlow Shapley, who at this point was now the director of the Harvard College Observatory. And he said, "You'll be interested to hear that I found a Cepheid variable in the Andromeda Nebula. I've followed the nebula as closely as the weather permitted, and in the last 5 months have netted 9 novae and 2 variables." What does that mean he's about to determine for Andromeda? The distance. In effect, he was telling Shapley, I'm about to prove that you were wrong, that the Milky Way is the entire universe. Here's a heads up for you. Get ready, it's coming. Very polite of him. All right, we answered that question. Why is that a big deal? So here's Andromeda. This is our neighbor galaxy for which he measured the distance through that Cepheid, but not quite yet. Here's the guy I like a little bit more because it's the Vanderbilt connection to all of this. This galaxy, NGC 6822, was discovered as a fuzzy little cloud by E. Barnard, first astronomer at Vanderbilt. And he did this in 1884 at a telescope that's just outside of Rand, the student center on the other side of campus. And there's a plaque right where that telescope was. So this galaxy was observed for the first time and identified here on the Vanderbilt campus. What Hubble did in the years 1923 and 24 is he found 15 variable stars in NGC 6822. And then of those, he found that 11 of them were Cepheids with periods ranging from 12 to 64 days. And from that, he determined the distance to this galaxy. It's now known as Barnard's galaxy, 700,000 light years far away. Here's his data for those variable stars. And this is his paper published in 1925 in which he writes that this is the first object definitively assigned to a region outside the galactic system. This is the first object we know that's not part of the Milky Way. And now we know the Milky Way is not the entire universe. And Hubble then observed the Andromeda galaxy and a companion galaxy to Andromeda in the same period of time and identified that Andromeda is 1 million light years away. And now the universe has gotten bigger. But all you need is a Cepheid variable star, and you can get the distance to these distances to these objects. So the spiral nebula debate ends again with the Milky Way being a galaxy and the universe being full of galaxies. That the spiral nebulae are galaxies like the Milky Way, collections of billions of stars. Hubble immediately becomes the major force in American astronomy, really in world astronomy. He presented a paper at a January 1st, 1925 meeting, although he didn't actually present it because he was in California. The meeting was in Washington, D.C. So Henry Norris Russell presented the paper for him. It was awarded the top paper for that meeting. He got a $500 prize, and now he can do anything he wants. Okay? So what he wants is to observe galaxies. This is a modern Hubble Space Telescope picture of galaxies. What should galaxies be doing? Galaxies are massive clusters of stars, each one billions of stars, lots of mass. So here's a galaxy with lots of mass. And over here's another galaxy with lots of mass. What should those two galaxies now do? They should be moving toward each other because mass attracts. So the obvious thing to do to demonstrate that is to measure their motions. Astronomers use what we call red shifts and blue shifts to measure the motions of galaxies. It's the same principle that police officers use to give you a speeding ticket. Okay? All you need to do is measure the red shift or the blue shift of the light from the galaxy. That gives you the velocity of the galaxy away from you if it's red shifted, toward you if it's blue shifted. So galaxies should all be blue shifted. They should all be coming together. And they're not. They're all red shifted. They're all going apart. And this makes absolutely no sense based on the conclusion we just drew that big things made of mass should attract each other and come toward each other. Hubble decides we need more information. He has redshifts, velocities, for 46 nebulae. He needs more information. He decides to go after distances because he knows how to measure distances. And in fact, he found distances for 6 of them using Cepheids. This is exactly what Shapley did for the globular clusters. Shapley got 5 globular clusters, and then he used other techniques with the Cepheids to bootstrap his way to distances for other clusters. So Hubble has the same deal. He's found Cepheids in 6 of the clusters. He now knows distances to 6 of them. He then demonstrates that the brightest stars in those 6 galaxies are equally bright. And therefore, he can find the brightest stars in other galaxies for which he doesn't have Cepheids, and he now knows the distances to those. And when he does that, he gets a total of distances to a total of 18 galaxies, 6 from Cepheids and 12 from those brightest stars. And he wrote a paper in 1929 titled A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. And this is the plot from his paper. The vertical axis is velocity, the horizontal axis, distance. The dots are the data points. The line is the fit, the relationship between the data points. The further away the galaxies are, the faster they're moving away from us. The closer they are, the slower they're moving. That's the relationship between the distance to galaxies and the velocities. Now, he only has 18 or so data points on this plot. And you'll notice this goes out to a distance of 2 million parsecs, 6 million light years. Pretty good distance. 2 years later, he produced this plot. All the data from the first plot are right here. He's now found distances to galaxies out to 30 million parsecs, 100 million light years. And the data all follows the same trend. The further away the galaxy is, I'll go this way, the further away the galaxy is, the faster it's moving away from us. Bizarre. This is the expanding universe. Now, I've got an equation here. I probably promised you wouldn't get an equation. So I lied, okay? Because you need this equation. This is known as Hubble's law, Hubble's equation. The velocity of the galaxy is proportional to the distance. H is the slope of this line, or it's related to the slope of this line. If you can measure the velocities and the distances, you determine the slope of that line. What I'm going to next try to demonstrate to you is this value right here will give us the age of the universe. All you have to do is measure this relationship. That's pretty neat. H is known as Hubble's constant. Okay. So why do more distant objects move faster? That's a question for us, and I'm going to give you 2 different ways of thinking about it. For getting an age of the universe, it's not going to matter. For understanding the universe, that's a more profound question. It does matter a bit. One method, which I'll call the bomb analogy. Space pre-exists. Space is just here. Just like this room was here before you folks came into it. You then entered the doors and populated space. So maybe space pre-existed the galaxies, and all the galaxies began at one spot, one location in space, and that location, all that mass blew up. And all those pieces flew through space in the same way you came in the door and spread out through this room. So we have our before picture over here. Each of the circles is a galaxy. Space just extends infinitely far in all directions, but there's nothing in that space. And at the first moment in time, this bunch of galaxies blows up and starts spreading apart like this. Now, the arrows are meant to illustrate the velocities. What would you find here after the explosion? Boom, it's exploded. Which objects will be furthest away from the center? The ones going fastest. The ones that are going slowest will be close. So in this analogy, you will get the Hubble relationship. The most distant objects will be going fastest. The slowest objects will be going slowest. And all of them will be expanding away from a particular location, the center of the universe. And in this model, there is a center of the universe. Right there. Right. The fastest pieces fly farthest, slowest pieces fly least far. We get the Hubble law, this relationship between distance and velocity. So here's our second way of interpreting this information, and that is expanding space. And this is weird, okay? But it's what we think is the right answer. Okay? In this explanation, galaxies are located at a particular location. The same way each of you is in a seat, the same way a chess piece on a chessboard is in a particular square, and they're not going to move. They don't move. You stay in your seat. The chess piece stays in its square. But I'm going to stretch the chessboard. And if I stretch the chessboard, the distances between the pieces on the chessboard will increase. So in this explanation, the galaxies don't move through space. Space is stretched. In this one, space doesn't change, but the galaxies move through space. And here's the cartoon for the second one. We have on the left piece of paper, if you will. And I have 5 dots on the piece of paper, A, B, C, D, E. And the little grid below it is meant to illustrate that the distance between A and B is 1 unit, 1 meter, 1 mile, whatever you want. Distance from B to C, 1 unit, C to D, 1 unit, etc. Now I'm going to stretch my space. A, B, C, and D stay in exactly the same locations in space, but the piece of paper gets stretched. It's now twice as big. So the distance from A to B is now 2 instead of 1. The distance from B to C is now 2 instead of 1. Yes?
Is there any significance if one's a rectangle and one's a square?
Bad drawing on my part.
Okay. Facing in different rights in different directions.
No, it wasn't supposed to. But I was only interested in making sure I got this right.
Okay.
But it should expand equally in both directions. Okay? So look at this set of numbers here. Before the explosion, or before the stretching, the distance from A to B was 1 unit. I'll call it a meter. Afterwards, the distance from A to B is twice as big, 2 meters. The distance from A to C before was 2 meters. Afterwards, the distance from A to C is 4 meters. The distance from A to D was 3 meters. Now it's 6 meters. So I can calculate now the velocity at which the different dots are moving away from each other. B is moving away from A at a rate of 1 meter per second if I went from the left hand to the right hand illustration in 1 second. Then the separation between them went from 1 meter to 2 meters. It changed by 1 meter in 1 second. So that velocity is 1 meter per second. From A to C, the distance went from 2 meters to 4 meters in 1 second. So the rate of change was 2 meters per second. The distance from A to D went from 3 meters to 6 meters in 1 second. So the distance increased by 3 meters in 1 second. So the rate at which they're flying away from each other, 3 meters per second. The whole piece of paper, space, is stretching uniformly. But the more distant an object is from me, the faster it appears to be moving away from me. I get the same answer as I got with my exploding universe. Yes, ma'am?
Doesn't that imply that there is a boundary then to space?
Does this imply there's a boundary to space? No, only the way I drew it. I'm going to have A, B, C, D, E, F, G all the way out as far as you want it to go.
If it's stretched, though.
Well, you're suggesting someone has to hold the ends and stretch it.
No, I'm not. I was suggesting
You could have...
something on the other side of space.
No, these are really difficult concepts to wrap your head around, even for me. But you can assume, and there's no reason not to assume yet, space could be infinitely large. There could be no end to space in any direction, but it could still expand.
But then you have to think.
What's it? You want to? The real question you want to ask is, what's it expanding into?
No.
Not you. You wanted to ask that, but you didn't want to ask that. All right.
The real question I want to ask is, what's your definition of space?
Spaces, all of that stuff out there. It's the universe. It's the, yeah. Space is a tough thing to define. And in modern physics, space can't exist without mass. Mass defines the presence of space, and mass affects the shape of space. So you can't have one without the other. So by that logic, the first model of pre-existing space that I just put some mass into, that actually doesn't work very well from that modern perspective.
The redshift and blue shift that Hubble detected, wouldn't that change just based on which direction he's looking in the universe? I mean, you say it's all moving away from us. That implies we're at the center. I don't think that's true.
It's not true. In this model I've put down, if I simply decide to calculate the velocities relative A to B, A to C, A to D, A to E, the further the object is away from A, the faster it's moving. But let me do it from B to C. The distance from B to C was 1, and then it's 2. The distance from B to D was 2, and then it's 4. The distance from B to E was 3, and now it's 6. It doesn't matter what place I pick in my universe. Any location, any observer, anywhere in the universe will see that more distant objects are moving away faster than closer objects.
Are these redshifts, or is it something
They're,
left to right?
they're all redshift. In any direction I look, I'll see the same answer. And in fact, in any direction we look, we do see the same answer. Yes?
Space is what is expanding, and the objects are staying still, but it's moving in space. And everything would expand at a uniform rate,
Yes.
and that's the conclusion.
That's the conclusion. Space is expanding at this well, pre-1997, space was expanding at a uniform rate. But with the discovery of dark energy, it appears that the rate of expansion of the universe is accelerating. But I'm still in 1931.
I'm concerned about what is fixed and what is variable. And in this system, Cepheid seem to be at the basis for measuring. Do they ever move out of the instability strip? Would you always just have to measure them in globular clusters?
Cepheid variables will stop being Cepheid variables eventually, once they move out. They're going to be Cepheid variables for much greater lengths of time than a human lifetime. They're going to be Cepheid variable stars for millions of years. So the likelihood that we observe a Cepheid variable today that will stop being a Cepheid tomorrow is pretty unlikely. So we can be pretty certain that the ones that we're observing are pretty steady in what they're doing. I've just got a couple more minutes. I want to get you an age for the universe. Okay? So let me try. Okay? Both of these explanations bring you to one conclusion that's identical. It doesn't matter whether you think stuff is expanding through space or space is expanding. Both of these conclusions say there's a beginning to time. There's a moment when all of those objects were at the same place at the same time. And it doesn't matter whether space is infinite or not infinite. They were all together at the same spot at some moment. So all we have to do is run the movie backwards. We measure how fast they're flying apart, measure how much time it would take them to get back together, and I want to illustrate that with a Google map. So we have cars on the interstate heading to Knoxville, and I'm going to give you some numbers. But in this case, I've got a car driving 65 miles an hour on I-40. Knoxville is 195 miles away. How long is it going to take him to get to Knoxville? 3 hours. At this speed, 3 hours. Don't stop at the rest stop. Okay? 3 hours. So again, what we have is the same equation. Velocity is distance divided by time, or time is distance, 195 miles, divided by 65 miles an hour. You get 3 hours. There's a relationship between them. And the time is the Hubble constant. The time is the relationship between distance and velocity, provided the velocities are steady. Okay? If you slow down and speed up, it doesn't work. But if the velocities are steady, you get this. And you get 3 hours for that driver. If I have 3 people headed from Nashville going east, Tom's on foot running at 6 miles an hour, pretty fast runner. He's now 30 miles from Nashville. How long did it take Tom to get 30 miles away? 5 hours. Dick's on a bicycle going 12 miles an hour. He's now 60 miles away. How long did it take Dick to get there? 5 hours. Harry's in a Mustang going 100 miles an hour. He's now 500 miles away. How long did it take him to get 500 miles away? 5 hours. The more distant objects give you the same answer as the close objects. If everybody started at the same moment, and the more distant objects have greater speeds, but you get that relationship whether the whole universe was something that exploded or whether you have all those objects at fixed locations and it expands, because we measure that same relationship. So for our bicyclist and runner and Mustang driver, we get 5 hours. For the Hubble law, H is going to give us the age of the universe, and when we do the mathematics, which I'm not going to make you look at, but when we do the mathematics, you're going to get the age of the universe from the Hubble constant, and that age is 13.5 billion years. It's just like the 5 hours for measuring the speeds at which these guys are driving away from Nashville. It's the exact same relationship. What we really get from the Hubble constant is a number with funny units, 73.8 kilometers per second per megaparsec. Okay? But that's the slope of the line, and when you do some conversions to turn that into years, 13.5 billion years, which is consistent with the age of the white dwarfs. It's consistent with the ages of the globular clusters. 3 different methods that all give us the same age. So the universe may be starting to accelerate, but it hasn't accelerated so much that the velocities no longer are close to being constant over the age of the universe. We can still get an age of the universe this way. But things are changing now. Question?
Well, my question was the uniformity that was being assumed in that year, was that just an assumption that arose out of being human?
The uniformity that arose in the year Hubble made his measurements, or in any year? For us,
In other words, in that year that all this was thought of.
okay, for us, the human lifetime is so short compared to the ages of stars and the changes that take place in stars that for all intents and purposes, it doesn't matter whether you make these measurements in 1931 or 2031 or 25,000,031. It's going to give you the same answer.
Still looks uniform.
It's still going to look uniform. Yes.
So he did have some facts that suggested to him uniformity, and maybe also a predisposition to thinking.
He had facts and predisposition to thinking it was uniform. Yes. The measurements he made clearly give you the answer. It's uniform. If I look in that direction, I get the Hubble law. If I look in that direction, I measure distances and velocities of galaxies, I get the Hubble law. If I look in that direction, I get the Hubble law. And in any direction, I get the same Hubble constant. I get the same age of the universe. The philosophical part of this that's so interesting, which we don't have time to get to today, is that it doesn't matter where in the universe I might be as an observer. If I were in the Andromeda galaxy, or if I were in a galaxy 20 million light years away, if I look that way, I'll get the Hubble constant. If I look that way, I'll get the Hubble constant, and I'll get the same age of the universe. It doesn't matter where I am in the universe. I'm going to get the same answer. I cannot today go to other parts of the universe to prove that to you. Okay? But philosophically, I can prove to you that it's absolutely unacceptable to believe in a universe in which that wouldn't be the case. But we don't have time for that, so I get to close by saying, I can't tell you about that today. All right? But we have one more meeting next week. We're in the building behind us. There are handouts on other books if you want to read other books outside. And the bookstore folks may be out there, and I'll see you next week.